Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and very good morning. Okay, kita start dulu dengan bacaan kita Al-Fatihah. Alright, so today we will continue our lecture. Alright, so far we have covered about the stellar evolutions and until the main sequence. So basically, when we talk about the main sequence, we know that inside the core of the stars is actually contain a hydrogen. Okay, and then we move on to the another stage of the after the main sequence, which is a post main sequence. And if you look through this, right, we know that from the luminosity classes versus maybe the luminosity classes here, we can have several stage here. The first one is actually instead of the main sequence, we do have the giants, right, and then the supergiants and also the white dwarf. But in this case, right, the luminosity classes are divided into few classes, which is 1A, 1B, 2, 3, 4, 5, and 7, okay, for the white dwarf. And we can see that it takes a long of time, right? It's a billion years. And seems the main sequence is actually to have the wide range of the parameter of temperature and also in terms of the size, okay? Right. So we move on to the post-main sequence here. And in this case, we have several stage or several part of the evolutions. The first one is what we call as the red giants. Second one is asymptotic, asymptotic giant branch or HEB, and the third one is actually the horizontal branch. Okay, so if we focus on the red giant, so this is the schematic diagram of the red giant, we can see that after the hydrogen, right, and once the helium is dumped into the core, so this is what we call as a red giant. Okay, so once the helium is dumped into the core, and this is what we call as the red giant, and it is have a very rich of the heliums inside it. Okay, and in this stage, we can see that the size will be increasing. Okay, so it do have the cool temperature, but it expanded, right, in terms of the size. And where is the hydrogens go? So it will go to the surface or the outer envelope. So we can see that the hydrogen is still have, but somehow it's not inside the core anymore. It's actually inside the envelope. Okay, so you can see the part of the envelope here, which is reached by the hydrogen. Okay, so we can have also the hydrogen burning shell beside the core, right? So in this case, of course, there is a difference between the envelope and also the shell. And in this case, we can have the increase of the radiation pressure. Okay, so there is a few activities inside the red giant. Okay, so what happened for the giant branch here? So we can see that um, if we compare to the size of the sun, yeah. So once the suns become the red giant, the size will become 100 times from now. Okay, so this is very, very huge. All right, it's also will be near with the Earth, our Earth, right? So it means that when the suns becomes the red giants, so the radius will be approximately 0.5 AU or 0.5 astronomical units, and this is actually 100 times current in size. So it is really, really big, yeah. And of course, we cannot think what happened to our Earth anymore. All right, it must be very, very high temperature, right? Even now, also we can face even the decreasing is about 1.5 degrees Celsius. We can see it's very hot for us, right? So just imagine if the suns become as a red giant, of course, our we cannot live inside the earth. Yeah, so this is the what happening when the suns become the red giant, and what happens when the main sequence runs out of the hydrogens on in its core. we can say that, of course, it will go to another stage of the Postmate sequence. And of course, as the most stages in a star's life, right, the exact Postmate sequence is primarily dependent of the mass. Yeah, so it's really based on the mass. Yeah, and we can say that we will look through the suns. Yeah, and then we want to explore what happened to the higher masses of the star. So please remember that the main sequence can be classified into two categories. Yeah, if it's above 1.5 solar masses and if it below of the 1.5 solar masses. Okay, so then we can say that it will move to red giant branch. Yeah, so the sun will move off to red giant branch as a example, and it will fusing the hydrogens into the helium, right, inside the hydrogen sharpening. And there is a very short helium flash happen, right? When the star move along the horizontal branch or HB, yeah, HB stage. So we can have the helium shell burning starts, and the star also move up into the AGB or asymptotic giant branch. Okay, so of course, the stars will remain on the space sequence as long as the hydrogen inside it, inside the core, and it will also fuse the heliums, right? But in this case, we can have the constant energy output, yeah, quite continuous. It's not, it's quite stable, yeah, instead. And mid-sequence stars also have the luminosity which is increasing slightly, and this is based on the expanding or the increasing of the size, yeah, because of its outer layer cooling. Okay, so we can have a evolution in terms of the size, yeah, for this part. And we can have the hydrogen fuels inside the core runs out, and the fusion will stops, yeah, shutting off of the outward radiation pressure. So we can get, and we can see that inward gravitational attractions here, which is causes the helium's core to contract, and it will converting, yeah, it will converting the gravitational potential energy into the thermal energy. So we can see the formations, yeah, difference, then, and also the mechanism of energy happen in this stage. Yeah, it will change the form of energy from the gravitational potential to the thermal energy, and the fusion is no longer taking place. Okay, the rise interaction will happen, and the core is still hot enough to fuse the hydrogen. Okay, and it will producing more energy when it was a main sequence stars. So this is what we call as a shell burning causes, yeah, which has a very interesting effect, because it happens suddenly, and it will fuse, and also it will form the shell. Yeah, so this is quite tough, yeah, instead of the core process. Okay, so we can have the increased radiation pressure, yeah, actual causes of the outer layers, and it will expand to the maintain of the pressure gradients. And this expansion and cooling causes the effect temperature to drop. Okay, so we can have, that is the reason why does the temperature drops, yeah, because of the increasing of the size. Okay, and of course, the luminosity will be eventually increased, yeah, in this time, whereas it can up to factors of thousands, yeah. So imagine from one solar mass or solar luminosity, and now it become to up to 1,000. So it will be increasing quite high in this stage, and the star will move up to the right on the HR diagram. All right, so we go to the Postmate sequence, which is red giant branch or RGB. And in this case, in terms of the luminosity and in terms of the spectral class, there is a class of high K, H, um, class K, and also low M, yeah, in terms of the spectral class, with the luminosity class of 3. Yeah, this is a class of luminosity classes. Okay, and of course, red giants have a very extreme, yeah, in terms of the density, and it will held by gravitational force, yeah, to the rest of the stars and easily ejected. and the mass loss from the giant is typically about 10 power of negative 7 to, in this case, compared to only 10 power of negative 17 during the main sequence stage. Yeah, so we can see that the mass loss is actually will be decreasing, yeah, in this increasing in this stage. So we can have it's about 10 power of negative 7 compared to negative 17, yeah, 10 power of negative 17 during the post-main sequence, main sequence stage. Okay, and of course, the envelope will be thinnest and also cool. Okay, and this is about 1/3 of the original size. Yeah, so in terms of envelope, is 1/3. Okay, and in this case, what happened is the electrons within the core will form a degenerate electron gas. Yeah, because the temperature will be decreasing, and they are packed tightly together, yeah, in a volume, okay, governed by the uncertainty principle. So this is based on the Max Planck, yeah, um, which is we do have the uncertainty principle. So it's about mechanical quantums too, okay. And this is no longer behave as the ideal gas because we are at the form of the degenerate electron gas, okay. All right. And there is a helium burning, okay, and also the helium flash, whereas we can say that what happened is the hydrogen fusions in the shell produce more heliums, okay, and the core will up to the temperature of the core will up to 100 million Kelvin. Yeah, so just imagine when the core becomes 100 million Kelvin, and in this time the helium nuclei now is sufficient, yeah, kinetic energy to overcome their strong Coulombic repulsions and fuse together, and this will form the carbon 12. Okay, so to have a formation of carbon 12, it means that we need to have the core temperature is about 100 million Kelvin. So this is a very, very high temperature. And of course, as the three helium nuclei, which is named as a particles, alpha particles, and this is what we call a process of the triple alpha process. Okay, and in this case, yeah, subsequent fusions with another helium nuclei will produce the oxygens, yeah, oxygen system nuclei, and this process is the main source of the carbon and also the oxygens found in the universe. Yeah. So we can have whereas now we know how does the carbons and also the oxygens form from the universe. Okay. All right. So this is the example of the schematic diagram of the triple alpha process. So we can see that there's this combination of the two heliums here, whereas it will have the reverse reactions to become a baryons, yeah, 4 baryons, and it will combine with the another helium again, all right, to produce a gamma before it form the carbon 12. Yeah, so of course this is needs about 100 million Kelvin of the temperature inside the core, and after that only this carbon 12 will be combined together with the heliums again, and it will also produce the gamma photons, and at the same time it will produce the oxygen. So we can have the combination of the oxygens and also the heliums plus with the gamma rays, yeah, at the end of the stage. Okay, so we can have the unstable process also and the stable process in this stage, and before it move up to the stable process, yeah, which is produce the heliums and also the oxygen. So this is actually what we call as a triple alpha process. Bear in mind, yeah, we have another process where we call it as a uh, CNO cycle, and also hydrogen, yeah, hydrogen change. So we can have another based on the solar masses and also based on the mass of the stars actually. Okay, all right. So this is a good example of the HR diagram that shows the post-main sequence, yeah, and it do have the process of the red giant, asymptotic giant branch, and also the horizontal branch, yeah, at the same time. So we can see once the stars move from the main sequence, all right, and it will go to the red giant branch, and this is a process where the core will become the helium inside it. Yeah, before that is actually the hydrogen, and then once it move to the giants, yeah, what happened is also we form the carbon plus oxygen. Yeah, and in this case there will be a formations, we call it as a horizontal branch or HP. And what is so interesting about HP branch is it will produce a helium flash, yeah, at certain stage or certain times. And this is takes a long of time before it move up to the AGB or asymptotic giant branch. So we can have a few process here, okay, and of course it's totally based on the mass of the stars, and some of the stars will just become as a giant, but some of them will move up to the supergiants. So we can have, if the star becomes the supergiant, so what happen is still the helium will move and form the carbon to and also the oxygen, but the size will be increasing. Yeah, and of course there is also a certain process and interesting effect that happen inside the supergiant, and it also have a several process before it move to the white dwarf. Yeah, so it will takes a billion of years before it move to the white dwarf. Okay, all right. So we can have also here, yeah, uh, the schematic diagrams that shows um, asymptotic giant branch here. So if, yeah, the stars or the giant star expand again and up to 1.5 AU. So this is actually equivalent to the orbit of the Mars. So just imagine if the sun become as a AGB, so of course the Earth is not anymore here, all right, because it move the sun is very huge, and of course it will eat actually the Earth, yeah, itself, and we can have AGB, which we do have the luminosity is about 10,000, yeah, compared to our current sun. So this is very we call it as a very strong brightness, yeah. So you can just imagine like the sun now is on, we can see only a white color, yeah, in terms of the luminosity, because the luminosity is about 10,000 luminosity current based on the our sun right now. So there is also a few stage here or evolutions. Is state of the core. Yeah, what happened to the core? Now the it's not just it's not the helium anymore, but somehow the core inside is actually contain the carbon and oxygen core. Yeah, but no fusion. And then the helium now will form at the burning in shell. Yeah, so we can have the helium burning shell outside the core, and we do have also the helium layer, okay, after the shell, and then only we do have the hydrogen burning shell after the helium layer. So so that is the stage of the AGB. So the AGB hair radius is about 1 to 1.5 AU, astronomical units. Yeah, okay. So how about the horizontal branch, yeah, or HB? So once now we have covered so far about the giant, yeah, and also the asymptotic giant branch. Now we move to the horizontal branch. So in this case, what happened is the energy we released by the helium flash and raise the core temperature to the point where it's no longer degenerates. So we can have that it will start again to be the ideal gas, and it will expand and cool, and the energy will transfer results in the hotter outer layer of the stars, but a small overall size. Yeah, and of course there is a increasing of the temperature, but the decreasing of the area. So it's not increasing in terms of the size anymore, but it will be slightly decreased. Okay, for the case of the HB. Okay, and these HB stars have the helium core burning, yeah, helium core burning, and also the hydrogen shell burning. So we can have the sufficient helium fuel for the core burning to last about 100 million years, yeah, for the case of the horizontal branch. And in the case of acidotic giant branch, yeah, take note again that we do have the about 100 million Kelvin um, to fuse, yeah, the in terms of nuclearization process, and in the star of the 8 solar masses or less, yeah, there is a insufficient gravitational energy to generate temperature required. Yeah, so there is no more core fusions, and the core recontractions does, however, will generate sufficient heat for the surrounding layer. Okay, so this is the case of the AGB. Okay, so I hope that you can differentiate between the red giant branch, yeah, the AGB and also the HB. Okay, so this is to stress again what happened to the AGB. All right, the giant star will expand about 1.5 EU, and it do have about 10,000 luminosity of the sun, and one of the example is a Mira or OCT. Yeah, so this is one of the example of AGB stars. Um, it might be in, a few examples out there of the AGB star, but this is a very popular one. Yeah, Mira is one of the AGB stars that quite near and popular. Okay, so this AGB, yeah, it do have the S process, which is a slow process, and also a rapid process. So this is actually happen, yeah, for the massive stars, and it also produce a thermal pulse, yeah, and but somehow only we are luckily because this thermal pulse is every 10,000 to 100,000 years. So it's not easy to get the thermal pulse or to observe the thermal pulse here. Okay, so AGB will also carry materials here, which produce in the thin helium shell up to the surface. And of course, we do have the rate of loss mass about 10 power of negative 6. Yeah, so we can have from 10 power of negative 17 up to 10 power of negative 7, and now it's about 10 power of negative 6 solar masses, yeah, in terms of the mass loss. And of course, as the stars evolves, yeah, up the AGB branch, the pulsation increase rate mass loss is about 10 power of negative 4 solar masses per year. Okay, this is process where it ejected the materials comprised in a mixture of the elements, yeah, including the carbon and oxygen, and also it do have the carbon-rich molecules, and in this case, the clouds will expand and cools, but the dust absorb and re-emits radiations, yeah, especially in terms of the longer wavelength. Okay, and this AGB, of course, more luminous because we know this is about 10,000 luminosity, and it can be observed in infrared, yeah, compared to the visible waveband, and it can carry up to 10 magnitude. So we can see the light curve happen for this kind of the AGB. Yeah. So this is one of the examples to shows what happened inside of the supergiant on its last day. And in this case, we have the ferrum inside the core, and we do have also the sulfur and also the silicon shell, yeah, after the core, and also the shell of the carbon and so oxygen. So it's almost a shell, yeah. Once is the last day of the supergiant. So we do have the helium shell, we do have also the hydrogen shell, yeah. Before there is a supernova that exploded on its last day. Okay, so this is a schematic diagram, but not into the scale. Yeah, but it just want to show what inside. Yeah, and what kind of the layer that have inside the supergiant. Okay, all right. So this is also to show what happened instead of the comparison of the temperature. We can have a potopotent chain, which is convert and specifically for the low massive stars, And we do have also C and O cycle, so much massive. And also we do have the triple alpha process. Of course, it needs a lot of and also a very high temperature for the triple alpha process compared to the proton chain and also to the C and O cycle, right? Okay, so I think that is about the lecture for today. Okay, we will continue the proton change in the next lecture, alright, inshallah. So with that, thank you very much and Assalamualaikum warahmatullahi taala wabarakatuh.